Hello and welcome to SETI Live. I'm your host, Beth Johnson, Communications Specialist here at the SETI Institute. Thank you to all of our viewers joining us from around the world. Please let us know where you are watching from. And also welcome into listeners of the podcast version of SETI Live, which is available now on most podcast platforms. Thank you for listening. A few weeks ago, we told you how a team of scientists and engineers from the SETI Institute, Impossible Sensing, NASA JPL, and several other institutions would test their innovative robotic laser system on a deep sea expedition aboard the EV Nautilus. The mission aims to advance technologies to explore, characterize, and sample the seabed here on Earth. On May 16th, the Nautilus left port and headed out to sea. Now, with several successful dives complete, I am joined today from the ship by research scientist and project lead Pablo Sobron, and from LPI, organic chemist and data scientist Laura Rodriguez. Thank you for joining me today.
Hey, Beth.
Hi, thank you for having us.
Thank you for being here. It's so exciting to have you from the ship. This is amazing. Look at that back there. Pablo, what are we looking at?
Yeah, so I'm going to turn around a little bit so you cannot see the screens here. So what we have here is a ship that is essentially tasked with exploring the subsea. And for that, it has a robot that you can see here. That yellow box that you see on the back, that's called an ROV, which is a remotely operated vehicle. And this vehicle is controlled remotely, as the name implies, from right behind from where I am. So remember all the NASA missions with mission control and Houston. This is our Houston. So here, when we launch the dive, when we send the robot down into the seafloor, we operate everything from right behind me. All the screens you see in the back. Scientists sit there. Pilots, navigators sit on the front row, and they have the joysticks and all the controls to operate the system. And one of the benefits of being able to do that is that because we're just literally on top of the vehicle, we are 1 kilometer or 2 kilometers away from the vehicle, we can communicate with it through fiber optics. And by that, we're able to really have telepresence in real time. So whatever the pilots are doing, the robot will follow immediately. And that way, scientists can get feedback on what's happening there, taking pictures, taking samples, deploying our technology, and any activity that we do subsea. So this is where the magic happens. This is where all the effort that all scientists pay to get their samples and their science happens all right behind me here.
Fantastic. So you guys left on May 16th. So you've been out at sea for a little bit. Have you gotten used to being out at sea? I know for me, the first couple days were incredibly rough. So how are you holding up?
Yeah, so like you and like most people that are not at sea all the time, we need a little bit of a period of adaptation. And you can use some drugs and or just rest and take it easy. And but yeah, it took a little bit of effort for everybody to get used to it. And part of the challenge is that we are essentially on the equator. And this is an area where all the weather systems form, most of them, and we have pretty strong easterly winds in this time of the year. So the seas can be rough at times. So traverse here was a little complicated, and doubly complicated because along the way, part of the mission is tasked with mapping areas that we never mapped before, and the ship has under the hull a very sophisticated sonar system that can take very high resolution images of the topography of the seafloor as it's moving around. So sometimes instead of moving and taking the easiest way into our destination, we are doing zigzags. And we are coming back and forth against the wind sometimes and different positions to get the best maps we can. And that sometimes is at the expense of our comfort. So, but I'm happy to say that after a few days, everybody here was really sharp and ready to work. No problem. Yeah.
So just out of my own personal curiosity, how many shifts are you guys working on the ship?
So we have the main ship where I'm sitting, the Nautilus, and then we have two ROVs, two robots. One is called Hercules, and that's the one you see here in the back. And the other one is called Atalanta, which you may be seeing it right here under the A-frame of the ship. The Atalanta is called a tow-sled ROV, meaning that this is the relay system between us here and the Hercules ROV. So it's a smaller AUV that is able to do several things. One of them is to film and take images of Hercules as it's working subsea, but also communicates power and data from both the ship down into the ROV and from the ROV up to the ship here. So we have two ROVs at any given time when we deploy.
And where is your instrument? Where is the InVADER? Where is it located at?
Yeah, so our instrument, unfortunately, you don't see it here in the pictures, but if you look at Hercules, the ROV here, that is trying to play with the direction here. So this is the front of the vehicle. Our system is in the back of the vehicle, so it will be somewhere right on the back there. And what it is essentially it's a tube. Think about a poster tube, about 2.5 feet long by almost 1 foot wide. And that tube contains computers, electronic systems, lasers, cameras, and a pretty complicated system to control the temperature and control that all vibrations and make sure that everything is working in synchrony, so that through a window we can shoot a laser straight down into the seafloor from a distance of anywhere between 3 to 10 meters. So we can shoot directly under the vehicle, and we can scan the seafloor. We can scan sediment, scan organic material, life forms, and minerals on the seafloor as the ROV moves around. So that's why we chose to sit on the back of the vehicle, so that pilots could have full visibility on the front. And all we do is essentially measure a little bit behind, right, from the pilots are seen from the front camera, essentially 2 meters away, and we can know exactly where we're shooting, because the Atalanta, as I said before, the other ROV, is seeing our laser as we're shooting. So we have a very good understanding exactly of the points that we're scanning, so that we can now correlate our measurements, which were first really in oceanography. We can correlate these measurements now with exactly where they were taken, and that way we can start understanding the performance of the technology, start doing science. And I think that's where today with me I have Laura Rodriguez here, which is one of the scientists in our team. And although she's working from not the boat, as you can imagine, you see her there with a nice steady state system. Nothing's moving there, but Laura is doing a lot of the scientific work that we do here. So you think about our team here is composed of myself and Kevin Sack, which is an engineer from the University of Washington Applied Physics Lab, and both of us are the robots, if you want to think about Mars, right? So we are the rovers, and we deploy, we do the things and tasking, and we have scientists back home telling us what to do. So one of them is Laura here. So I'll let Laura maybe explain a little bit about the science that we do and how we do it and why it's important.
All right, Laura, I do want to get to know you really quickly. I want to welcome in a whole bunch of people because I'm seeing tons of places here. So let's welcome in our viewers. So we're seeing people from Portugal, Scotland, I think that's Finland, Puerto Rico, Chile, Dhaka, England, South Carolina, more United Kingdom, Connecticut, Washington State, Georgia, the state of Georgia, Berlin, Washington, D.C., South Carolina, Florida. You guys are really making me work on my flag knowledge. I don't know what that one is. Peru, Philippines, Colorado, Uruguay, Arizona. Oh my gosh. I know some people are actually watching from Atlanta, Georgia. More Colorado, Israel, New Jersey, India. Wow. Okay. So from all over the world, thank you everybody for tuning in. Laura, you're a scientist on this project. What are you working on? What are you doing? What is your role here?
Yeah, so my role has been more about looking at, I kind of approach it from the interest of what we can get out of these types of techniques when we want to go explore oceans on other planetary bodies, so ocean worlds. And we're really interested in that because those worlds, like the moon of Jupiter, Europa, or the moon of Saturn, Enceladus, we think have all of the conditions needed for an origins of life event and to support life. And so they're very interesting places where we want to explore, and exploring oceans is very difficult. And so this project is looking at taking techniques that already have some mission heritage and are being used on other planetary missions, such as the Mars rovers, and seeing how well they do when you put them in a completely new environment, high pressure, underwater, and completely different systems, right? Now we're looking at hydrothermal vents and deep sea environments, which are very different from the environments you're going to find on Mars. And so some of the questions we're asking is, well, how well are these techniques at characterizing the organics and the geochemistry, the elements and the mineralogy? What can they tell us about the potential habitability and looking for areas that might be interesting for potentially hotspots for biological activity? And so we kind of are approaching it in that way. And it's really exciting because it's just, for one, deep sea environments, they're just exciting. And like Pablo's looking at a completely new environment right now, which is just super cool. But it's also really cool to think about the potential implications for this technology in future missions planned by NASA.
Fantastic. So Pablo, you're testing, you're actually getting to take your instrument down to the seafloor now. Tell us about some of the testing that you've done. What is entailed in a dive? What have you been doing? What data points are you collecting? Just give us kind of an overview of what's going on here.
Yeah, Beth. So we've done so much. I mean, it's pretty unbelievable that we came in here in a first, right? So this is the first time this instrument goes in the water. In the lab, it's been in the water, of course. We tested that everything works and pressure doesn't break anything. But it's the really first time that goes into the real world, right? So going from the lab to the real scenarios, a lot of things can go wrong, and they're wrong all the time. So for us, we approached this mission with caution, right? So we knew that it was a very first time that we could, play with our toy, if you want, in the ocean. So we had a pretty not conservative, but I mean a pretty realistic set of goals, which was as soon as we go in the water, let's turn it on, flip the switch on, and make sure that everything works, right? That was the first thing. And believe it or not, there is reasons to believe that some things wouldn't work, again, because this is very, very complicated technology. It's taking us 5 years to build, and it's really not different than the way we do things on Mars, where, no matter how much you test, no matter how much effort you put in beforehand, once it's off, a lot of things are going to go wrong, right? So anyway, none of them went wrong, fortunately, and so far, I'm going to keep knocking on wood, we haven't had any single point of failure. Instead, what we did off the bat, as soon as we touched water, is start measuring the water. Although our goal is to really measure the seafloor, measure biology, ecosystems, habitats, and minerals that happen with them, we said, well, might as well just look at the water. And we know that water, the water column, right, changes from surface to the bottom. Temperature goes, in our case here, from 28 degrees to 2 degrees Celsius. Pressure goes from 1 atmosphere to 1,500 meters, how far we go. And salt level change, organic level change. All the marines know that you see in the videos and the pictures, it dilutes as you go down. Anyway, a lot of things change as you go in depth. And we said, well, can we see those things? And so it was somewhat surprising that we could actually do it. But what we did is we scanned and we shot the laser every 25 meters going down. So essentially every minute. And we got a data point every minute, right? So, on the fly, qualitatively, we could see the response in our screen. So we have a laptop dedicated to see what the instrument is seeing. And what we see essentially are lines, right? So we something that you probably see in an EKG or something that you see a line with spikes coming up and down. That's what we see. That's our response, our instrument. So we're able to see how this changes over time as we're going down. So we got the very first scientific validation that, hey, we are sensitive enough to see changes in the water column. And here is the novelty and the spectacularness of this result is that today, to see these changes, scientists had to sample at every single depth, get water sample, and either take it up to the deck of the ship and do analysis there, or keep it in a jar in a fridge and ship it back home where you can do lab analysis. Or in some cases, with very sophisticated systems, you can ingest the water into a box down in the water and spend half an hour, 1 hour to get the results right there. So what we showed is that on the fly, in real time, in seconds, we can actually get probably not the best quality data yet because we're new still. Remember that this is the first time we dove altogether, but we already could see measurements, right? So that was one of the, I guess, best moments of my career in science, I think, when you actually prove that you can do something that you didn't even think you could do. We call this opportunity science. Right. So, and then as we went down into the seafloor in the first and subsequent dives, we have done 3 dives so far, of which we've logged 20 hours of operation, which is way, way, way more than I thought we could last. Think about the Mars rovers, right? The JPL gives you a guarantee of 2 years, and then you're on your own and it's going to break. Sometimes it keeps working, right? Curiosity, 12 years on and still going strong. So in our case, it's the same. We thought that we could last 2 to 4 hours, and we're now at 20 hours and still strong as well. So what we did is overall collected about 10 gigabytes of data, which means about 700 data points through these 3 dives. And these 700 data points are not just the water column, like I explained, but we also did what we call a traverse with the ROV. So the ROV has a waypoint map, and we can tell it to go to places. So what we ask to the navigators is, well, keep us at a constant depth of 3 meters, elevation rather, and just track the terrain. And we're gonna go behind, shooting laser as you're moving down, right? So so we were just essentially painting a line of measurements along a transect, and along that line, we were able to see for the first time again now organic pigments from some of the biomass that happens there. There are some hydroids, corals, there are some sponges, some other pigmented organisms there. We can start seeing the signals in our data, which was another, not a surprise, but it's another confirmation that this instrument performs even better than we thought it would in real world. And finally, we were able to see some minerals in the sand and the sediment, but also on the rocks themselves. And like Laura explained, like these systems in the past were very active. They were volcanic systems, and here that means that there is minerals that happen in this scenario. So we're able to see now fingerprints of this volcanic activity now expressed in these minerals. So for us, it's a really all in all full stack mission where we're seeing organics, we're seeing water chemistry, and we're seeing minerals in the seafloor. So 3 for 3, in fact. So we have probably 1 or 2 more dives, Beth, and we may just see something that we haven't seen before. So really excited to see if we can actually push the limits a bit more and see something else.
Congratulations. That is a huge accomplishment, and I'm very excited for you. So Laura, you're here on the continental US. You are not dealing with seasickness and rocking boats. What kind of data are you getting back? What have you seen so far in the data that you've had a chance to kind of go through?
I will say I did actually get to experience being on a cruise with Pablo. I think it was a couple years now. We went and we collected samples from a deep sea hydrothermal vent system. And the idea with that is, so part of the research is we're testing out the instrument in situ, but we also wanted to bring back samples from these environments, characterize them using the gold standard techniques in the lab, and then recharacterize them with the instrument, the payload, to see how well the payload does compared to these gold standard techniques. And so that's part of the work that I'm doing here on land now, thank goodness, because I got really seasick on the cruise. And some other questions that we're thinking of in terms of, because underwater exploration is it's very complex. It's not only ground truthing how well the instrument performs, but also trying to think about it from a mission operation perspective. So how many points do we need to get, for instance, of an environment to really capture the geochemistry? And, how well does it do at characterizing the seawater with different depths, for instance, because that could help you identify if there's suddenly a hot water coming out and it's surrounded by cold water. If you could identify that, that would be an interesting geochemical environment where you could potentially have some interesting biology happening. So that's also what I'm doing on land. And then the final part I would say is looking at data science techniques to really dig into the all of the data we're getting back. So this instrument can rapidly acquire a bunch of data. And so that can be very difficult to parse through manually, spectra by spectra. And so in a planetary mission, you would really ideally want to have something on board that could autonomously process the data and help reduce the size essentially, so that you could easily send it back to Earth, because that is a major constraint with planetary exploration of ocean worlds is they're so far away that we are limited how much data can actually be sent at any one time and how often the data can be sent. So that is another very important aspect of this science that we're looking at.
Of course, that makes sense. So I have more questions. I'm kind of getting them in my head here. If anybody in our audience who's watching has questions, please feel free to share those in the chat. We are monitoring and we are pulling the questions aside, so we will try to get to as many of them as we can. Laura, tell me how you got into science. I know my own pathway was a little jagged and a little weird. So how did you get here? How did you end up working in science in general? And how did you end up on this particular project?
I'd say, I guess I always had an interest in science. Growing up, I would like to look at the books of space, and I was just fascinated with pictures of space. And I was also really interested in like anime that were featured, aliens and things like that. So I was really interested into that. But when I went to undergrad, I actually didn't even consider planetary science. I was thinking more like, I am good at math, I will become an engineer. And I kind of was interested, I guess, more in being an astronaut. And then I took my first physics class and I was like, I do not understand. Physics just did not click in my brain for me like chemistry did. And so I realized I didn't want to be an engineer. I really liked asking more of the scientific procedure and doing actual like experimental lab work. And like I said, chemistry seemed to just click more easily for me. So I decided to go down that path. And I really got into the geosciences at that point because what I loved about it was it kind of just takes a little bit of all these different fields, biology and chemistry and geology, and you're able to dabble in all of these techniques to answer really complex questions. So that's what really set me down the path of organic geochemistry. And then from there, I learned about astrobiology just from watching it was called Through the Wormhole. It was a documentary and they had an astrobiologist. And I was like, oh my gosh, this is a thing that people do. People are actually looking to try to understand how life originated and if there's life on other worlds. And then from there, I was totally sold on the astrobiology. And that's what I decided to get my PhD in. And my PhD was really focused on organic geochemistry and all about how could genetic precursors form on early Earth. And towards the end of that, I started really getting more interested in mission work because it's really one avenue to benchmark and ground truth all the lab experiments the chemists are doing. Because we can go and we can see what are the organics present in these different worlds. And so then I got into planetary exploration and decided to pursue a postdoc at JPL with Dr. Lori Barge. And that is how I got involved with the InVADER project. And it was really different for me because my PhD was really more of the laboratory organic chemistry, and InVADER was more learning about spectroscopy and I really learning how to code and data science. And I got to say, I really have loved it. And that's one thing I've really loved about the whole process of being involved in planetary science is I keep learning new things that I actually love that I never would have realized how interesting and fascinating it would be. It's really taking my career, I think, in interesting directions.
That's incredible. I like that. My story has some similarities to yours, except that I actually did get my degree in physics. But to your point, my mother made the comment afterward, like, it's a good thing that you love physics. And I said, no. Physics was a means to an end. I love astronomy. I don't love physics. So yeah, I completely understand the no, don't like this.
Didn't click for me.
yeah. It's the route to planetary science for some of us. Yeah. So Pablo, you've been doing this for, as you said, like this particular project has taken you 5 years to get to this phase of testing. What are some of the biggest trials and challenges you have had getting to this point in this project?
Yeah, well, so how long do we have now? Kidding. A project of this magnitude, right? When you're doing a first in a field, in two fields actually, we're doing a first in space exploration, future, and a first in Earth exploration. So that means that off the bat, you have to rely on expertise from multiple institutions, multiple people. And that has its own challenges, right? Imagine, working together with government agencies, universities, research institutes, minority serving institutes, which was very, very interesting for us because we had to have new blood coming in and new perspectives in our project. So having a symphony of all these players together and have them play the song at the right tempo and the right pace, the right way, that took us a little bit of time to get used to that. Then, of course, came the pandemic, which in our case, beyond the personal toll that it took in the team, it is a problem of some people can go to the lab to advance the project. Some people cannot go to the lab. Some people are quarantined. Some others are not. Vendors give you what they promise you in time, or they don't. Right. So I think it was 2 years of a little bit of chaos in that we were essentially patching together the technology, and the tests as best as we could. But here is the I guess the upside of all that chaotic environment of coordinating different teams and people all over the world rather. So is that we got in touch with the ocean community on Earth here in a deeper connection than we had before. Of course, we had ocean scientists in our team from the beginning, but we were able to expand this because, as most of you, we're stuck home. All we had to do is to go on Zoom meetings and get to know people, a lot of new people, in fact, and that really gave us a different outlook on the project, right? And to me, that was really, another challenge, right, of trying to kind of tame my excitement about being able to almost pivot the project into a ocean project and not so much space, for the simple reason that I was learning on the fly how little we know about the ocean. And I've been working in ocean projects for more than a decade, but really didn't dawn on me that for all the work we're doing on Mars, on the Moon, and we pretty much know the surfaces of those planets better than we know what the seafloor looks like in our planet. And compounding now with climate crisis, energy crisis, food crisis is coming together. Start to realize that the ocean is really, really everything for it, right? It's a great source for food, kelp farm, algae farm. It's a great sink of atmospheric carbon if we do it right. We can trap a lot of the excess gases that we emit in the atmosphere. It's really been a vehicle for communication between civilizations since we have been civilizations. So, to me it was like, wow, how can we do both? How can we now explore space in future? How can we give NASA what we promised we will give them? But also, how can we really, really help ocean scientists learn more, faster, and cheaper about our own ocean, so that we can start making policy decisions and enable a really sustainable blue economy that we all wanna have. So that was the third challenge, I think, is that how do we combine and how do we really are able to align the interest of agencies like NASA, NOAA, BOEM is an agency that's looking at minerals in the seafloor. Even the Navy and the Department of Energy are looking for minerals in the seafloor, right? So how do we combine all these directives and mandates for the agencies so that they can keep supporting us? So that was the challenge that really luckily we overcame, and that's why we're here. Here we're in fact supported now by not just NASA, but all these other agencies that I listed, because they have a vested interest in seeing us succeed. Because as I said before, technology of this caliber, when you're doing new things for the very first time, it really opens possibilities in fields that you don't even know from the beginning. We didn't notice, maybe Laura did, but I didn't. When we wrote the proposal at the beginning, and when we were all thinking about this, it didn't occur to me that there is so much more we could do. So I think yeah, the people and teaming with a large organization, pandemic obviously, and then stay focused on the mission, right? While you have so many opportunities to really change the world, other worlds too. So
it's an exciting mission. It's an exciting time for you, I am sure. Just to remind our viewers, we are a nonprofit, and if you want to know more about what we are doing, you can head to SETI.org. You can make a donation if you want to support our outreach and our science, or you can just subscribe to our newsletter. It's called Journey. It comes out about once a week, and we keep you informed on this. And we send out links to things like the 24/7 Nautilus live stream that is happening right now for this trip. And you can see all of these things that are going on, and occasionally hear Pablo give some commentary on what they're doing. So it's pretty amazing. I am going to take some audience questions now. This one is let's see. I want to start with this one. Are the pressures expected on a subsurface ocean like Europa similar or comparable to what we have here on Earth?
I can take this question. They're going to be a lot, it's going to be a lot more pressure on Europa compared to Earth's oceans because Europa's oceans are actually much more deep than the Earth's ocean. And so as you get deeper and deeper into the water, you have higher and higher pressure. And so the bottom of Europa's oceans where you might want to look at the seabed water interface or look for hydrothermal vents is just going to have much, much, much more pressure compared to that of the bottom of Earth's oceans.
Okay, that makes sense. Along the same lines, I think this kind of goes to Pablo. Would you consider integrating this technology into, say, the Europa lander or something to go on into Enceladus, something that can go under the water preferably? Was this something that would work in that field?
Yeah, in fact, this is the plan. The plan is to land on Europa or Enceladus or any other icy moons and figure out how to melt/drill through the crust of ice, and while keeping the technology inside the tube, perhaps looking at the side, right, on the wall as you're going down in the ice. And eventually, when you hit that interface between the ice and the water, then is when you release this system. So yes, RAN, that's your name. Yeah. So that's the goal, is to really do a combined mission, because frankly, a mission like that is going to cost between $5 and $10 billion to get there. We only have one shot, right? And in one shot, we're going to have to land, explore. Well, first of all, we're going to have to find where to land. Then we're going to have to safely land, explore around a little bit, and then pick a place to melt and drill, and wait anywhere from a month to a year or more to get to the ocean, and then only then we can deploy an instrument like ours over there. So yeah, that's definitely the path to flying this. Yeah.
That's the ultimate goal, right? It's planetary science. We want to get to the other planets and worlds in our system and find out more about them. For a question for both of you, and I think this is sort of a key here, is what in your opinions, this is from Catherine, what would be the most important thing for you to learn from this project?
Why don't you start, Laura?
Okay. So many things I want to learn. I think the most important thing would be to learn how this technology can be used to look for potentially habitable environments on ocean worlds, because like I said, they're the most promising, I think, candidate for finding other life forms. And so this technology allows us to go and actually identify where there might be ongoing geochemical activity, where there would be a lot of free energy for life to use. And so that is just the first step, because you can imagine, I mentioned, for instance, Europa. I mean, the ocean is huge. And so trying to find a location to focus where you would want to do additional analyses that are a little more sophisticated to look for evidence of life, you're going to be really constrained. And so you want to use those instruments selectively. And this technique, being very rapid, can help you rapidly assess your environment and determine, hey, this is an interesting spot. There seems to be a lot of potentially hot geochemistry that could release minerals and elements useful for life. And therefore, maybe this is something we would want to pursue for our other instruments.
Yeah, and for me, since Laura, as you can see, we're in good hands here. She's going to figure out all of those things. I'm going to go a bit more, I guess, almost philosophical, but I think what I want to learn about this is, can we speed up the pace of exploration of our own ocean here? And can we cut the cost of that activity? The way I look at the seafloor, the ocean, it's a giant barcode, right? And the way we're doing it now is we're picking up bars from the barcode randomly here and there and taking them to a lab and trying to put it all together. What I think I want to learn is this the barcode scanner that we were waiting for? Do we have a technique here that can you bring down there and scan the barcode in situ without having to bring it back to a lab? So that's, to me, the main question. Do we have the tool now to really speed up and make it cheaper to learn our own oceans?
I like that. From my own experience on a ship, I definitely understand the bringing up 50 cores, labeling them, getting them all back, and then spending years analyzing those cores. Being able to do some of that stuff without taking all of the materials from the seafloor would be great. Let's be honest. Pablo, I should have asked you this, but I kind of want to know, why were there only a few hours expected for InVADER to last on this testing mission?
But but there is many reasons for it. But the main one is that because we didn't need to test it for more than a few hours to learn what we had to learn from the first dive, right? So we're taking this technology development program at baby steps, right? So one thing at a time. And for us, the test was, okay, first time that we go, on a bicycle, right? So you don't go for the Tour de France the first time, right? You go for a little, run down the driveway, right? So for us, our driveway run was deep in the water, go to our maximum depth, which is 1,500 meters, make sure it works down there, come back, learn the lessons, and go back to the drawing board and make it better next time. That was exactly what we wanted to do, and we built it for that. We didn't expect to last longer because we didn't build it for that, and we didn't build it for that because we didn't have to. For us was the natural pace. So we're now, in fact, building 2.0. We're building the next version already, and it's gonna, likely, because we've been able to not break it in a few hours, we're learning so much that we're now able to bring these lessons learned into the design of this 2.0 version, which is going to be phenomenal. So can't wait to be, most likely next spring, we'll be ready to take the next evolution of this technology into another mission like this. So and that one, I promise you, it wouldn't be made for only a few hours. That one will build it to last for about a month on an autonomous vehicle, mowing the lawn, mapping around the seafloor on its own. So that's the next step.
Well, that kind of answered what I like to have as my final question, but I'm going to ask it anyway. So what's immediately next for the mission at sea, and for what comes after that? Pablo, for the mission at sea, what's up next? Do you have more dives planned, more data to collect? How's it looking so far? Yeah,
so our next 1 or 2 dives, and I think that's all we have left in the next week before we go back to port. Is that there is one. So to give an idea of what we're looking at here, so we have a technique that can measure 3 things, right? And one is it can measure molecules in water and minerals, so it tells you a little bit about what you're made of. It can also measure organic pigments, biology, ecosystems. But there is a third mode that we discovered, but we didn't discover, but we verified that it works here. Is mode that is called luminescence, that can actually, some of the minerals and rare earth elements can glow in the dark after we shoot them with our instrument. And we didn't think that would work, but it does work. So these minerals, we're excited about this because this is the metals that we need to build batteries, turbines, solar panels, even hydrogen technologies. All of these minerals, we don't have enough of them on land to really decarbonize the economy. We have all of them in the seafloor. So if we're able to find them and not only find them, but map them out, see how much of those we have, but also what ecosystems are around them, we can start finding areas where it will be safe to mine these metals in the seafloor, and areas that need to be protected as a national park of sorts. National monuments is how the US calls them. So to us, that's the next test. We're going to push the limits to see if we can find the manganese, the cobalt, scandium, yttrium. These sound weird, but these are it's called critical minerals, and this is what we need for batteries, turbines, or solar panels. So that's the next two dives. And moving forward, and I think this is something that will make Laura happy and all the scientists in our team, is with this very same instrument, we're not going to take it back and piece it apart. We're going to go back to these areas that Laura said we visited a couple of years ago, these vents, active chimneys where life may be thriving. We're going to go to those places that we visited 2 years ago now with this instrument, because now we know it works. And now we're going to be able to put it there and hopefully leave it for a year and have it there scanning and getting us data for the first time at high frequency for over a year of dynamic systems like vents, which we think that's where life might have started here. So I don't know, Laura, if you want to end a little bit on a why this is important for us to do next, then I think we'll be good.
Yeah, I think it's really exciting, especially, if we can bring back the payload to that site we visited 2 years ago, because that's where we had a lot of active hydrothermal vents, and hydrothermal vents are kind of like oases in the ocean for life. It's where you get a whole bunch of really cool biology in one spot, and so those would be a very promising location to look for life on otherwise, potentially sparse ocean on another world. And so it'd be really exciting to have InVADER down there and just consistently analyzing these sites, because one, it's very hard to monitor these sites. So you go, you get your samples, and you maybe go once, twice, every couple of years. And this would actually allow us to, like, in real time, monitor a hydrothermal vent system and see how it's changing throughout the year, which would be really important for ocean science, as well as just seeing how well this payload can be used to monitor biologic activity at these sites.
So for you, what's next, Laura?
Well, currently I think partly thanks to the effort we put into this project, I got a job as a staff scientist. I'm currently working at the Lunar and Planetary Institute. So I've actually taken a lot of the skills from I developed in this project, and was selected to become a Mars Science Laboratory MSL participating scientist. So I've actually been doing some operations on Mars using the ChemCam laser, which is very similar to the laser that was built for InVADER. So I'm doing some Mars operations, which is always really exciting.
Congratulations, that's huge, and you're getting ready for a move, and you have a lot of great stuff going on there. Fantastic. Pablo, when's your next dive?
Good question. I wish I knew. We're battling. You don't see it because I'm moving relatively to the ship, but I'm doing like this all the time. So we're in heavy seas now, and we don't know. It may take a couple of days or 3 days to do that. So I encourage folks listening today and watching, keep an eye on the links that I'm sure Beth will put here for you, to where you can watch us live. All the things that you see in the back here, they're being live streamed 24/7, including commentary from mission control. So when there's people here behind me, they're getting ready for a dive, deep dive. When people are here, all the talkie and chitty-chatty that goes here on how they're doing things, it's all live streamed 24/7 from the Nautilus. So it's super fun thing to do, and I think you're gonna have a lot of fun if we have time to do this. And we do this 24/7. So log in. Don't even have to log in. Just open the link, and it will show there 24/7.
Yeah, so it's just my favorite one is to watch the quad. You can switch to any of the camera views. There are 4, but if you switch to the quad, it's great. So you can kind of see everything that's going on, and the commentary runs on every single one. Again, it's 24/7. And when we find out that Pablo's doing a dive, we try to tell you guys as quickly as possible so that you can watch it. But keep in mind, how far down have your dives been so far, Pablo?
So the ones with our instrument, because we're maxed out at 1,500 meters, that's how far we've been. Other dives have gone all the way down to 2,500 meters, so mile and change. Yeah, so yeah, it's pretty deep. Yeah,
pretty deep, and it takes a while for it to get down there. So if you jump on right as they start to drop down, you're going to have a bit of a wait before they start doing anything very interesting. But you might see some cool stuff in the water itself. So always fun.
Well, in fact, Beth, yesterday during our dive, we saw an animal. It was three tentacled jellyfish, and I don't remember the scientific name of it, but I learned that this is the first time in 8 years that this animal has been seen. So it's a very rare occurrence, and so you blink and you miss it. So it just happened to fly across from our camera, and again, this really tells us how little we know about the ecosystems on there, that only we've been able to see this animal twice in the last 8 years. So yeah, there's fascinating stuff to see down there. Something that I learned is a batfish. It's a fish that is in the bottom, and it looks like a bat, and it has a little tail, and it's black. So
I saw a lot of I saw a lot of sea cucumbers and some Pacific octopus, which, by the way, seeing Pacific octopus in the wild, very amazing. But that you're getting to see some wilder stuff than I did.
Yeah. So yeah, while the 1 hour descent or ascent through the column may seem boring, anything but boring. There's all kinds of animals flying through, and they like the lights. They come in, and it's very interesting dynamic there. So it's fun, and you have commentary on that too. So that's the fun thing. Scientists here know the names of all of this, so you actually get educational real-time video. So pretty cool.
All right. Well, I definitely recommend that if you have a chance, go put the Nautilus live stream on in the background and just listen to what they're talking about. Believe me, if something interesting comes on, they will tell you and you will hear it. So it's just worth having on in the background. Pablo, Laura, thank you so much for being here today and for letting me take a little more of your time than usually planned. It was just such a fun conversation, and I'm very excited by this research. So I definitely want Pablo, I know you're going to be back multiple times to talk about what's going on with InVADER. Laura, please let us know what happens with any research that you're working on, and we would love to have you back as well. To all of our audience, thank you for watching. Thank you for asking questions. I know we didn't get to all of them, but I do know that today there is someone in the background in our production team who is actually taking down your questions. And so hopefully we will get some nice little videos from Pablo answering those questions on Instagram. So make sure that you follow the Instagram for the InVADER mission, and you'll hopefully see some of those things. Keep an eye on SETI's Instagram. We do try to share InVADER's and Nautilus's posts when we can, when they do involve our mission. So thank you, everybody, once again, to Pablo and Laura for being here. Thank you to Rebecca and Hesmine and Marianne in the background for handling all of the things. And thank you to the audience. Once again, this has been SETI Live. If you want to support SETI, please go to SETI.org and find ways that work for you to support our organization and our science. We'll see you guys next week. Thanks a lot.
Thank you, Beth, and everybody.
Thank you.